Hi everyone, here's the video for the Quiz 7 for Calculus 1000A. I'm going to go through some solutions to each of the questions. First question. What is the maximum vertical distance between the line y equals x plus 2 and the parabola y is equal to x squared? That's helpful, not necessary but helpful, to draw a picture of this. Let's see. Okay, so here's a sketch. X and y axes. Here's the line y is equal to x plus 2. So that's a y-intercept of 2, slope of 1. And then the next line, the next curve, y is equal to x squared. Parabola facing up. And from the picture, it's clear that for values of x between negative 1 and 2, the red line is on top. Okay, next. We're going to create a formula for this vertical distance, which I'm going to label with that red arrow. We'll call it capital D, and that's going to be equal to the y value of the top line minus the y value of the bottom line, bottom curve. Distance is equal to x plus 2 minus x squared. And we're looking for this, where this distance is a max. So this is a global max-min question with endpoints x is equal to negative 1 and x is equal to 2. We're going to check for extrema in the interior by taking the derivative of our function and setting it equal to 0. Derivative of x is 1. Derivative of 2 is 0. Derivative of x squared is negative 2x. We look for our critical points. We set the derivative equal to 0. 1 minus 2x. Move the 2x to the other side. Divide both sides by 2. We get one critical value of x is equal to 1/2. And because this is a global max-min question, we're going to check our function f of x at the endpoints and at our special point. F of 1/2. That's going to be, where's the original function? Oh, d of 1/2, let's say. That's going to be 1/2 plus 2 minus 1/2 squared, which is 1/4. And that's going to be, bring everything to over 4. We'll have 2 over 4 plus 8 over 4 is 10 over 4, minus 1 over 4 is 9 over 4. Okay, we also have to check at the endpoints. Check at negative 1. We're going to get negative 1 plus 2 minus 1. That's a vertical distance of 0. That's one of the points where the two curves cross. And then we'll check at 2. That will be 2 plus 2 minus 2 squared minus 4, also 0, another crossing point. So the max is at 1/2, comma, 9 over 4. You could also do a second derivative test to confirm that this is a max. Next question. We're asked to find the original function f of x, told that its second derivative is that quadratic, and told that the function, mystery function evaluated at 0 is 3, and the mystery function evaluated at 1 is 10. What we're going to do is we're going to integrate our second derivative twice. We're going to get the antiderivative twice. First time we take the antiderivative, we go from f prime, or rather from f double prime to f prime. Antiderivative of 4 is 4 times x. Antiderivative of 6x is 6x squared over 2. And then antiderivative of 24x squared is 24x cubed divided by 3. And it plus c, this integration constant. Before we integrate again, we'll clean this up a little bit. 6 over 2, that's 3, so 3x squared. And then 24 over 3, that's 8x cubed plus c. If one of the conditions was f prime of 0 is equal to 10 or something of that nature. If they gave us information about the first derivative, we could use that info to get c right now. But both pieces of info about the function are about the function, not about the derivative of the function, so we have to integrate, leaving that c there. The antiderivative of 4x is 4x squared over 2. Antiderivative of 3x squared is 3x cubed over 3. Antiderivative of 8x cubed is 8x to the 4 all over 4. Antiderivative of a constant is a constant times x, plus we get another constant, capital D. Okay, let's clean this up slightly. 4x squared, 4 over 2 is 2, so we have 2x squared. 3 over 3 is 1, so we just have an x cubed. And then 8 over 4 is 2, so we have 2x to the 4 plus cx plus d. Now we use some initial condition information. Told f of 0 is equal to 3. So 3, the y value of the function, is equal to, all the x's get replaced by zeros. So we'll get 0 plus 0 plus 0 plus 0 plus d. So that tells us quite clearly that d is equal to 3. Next piece of info. So that's f of 1 is equal to 10. So we'll have 10 is equal to, replace all the x's with 1. So we'll have 2 times 1 squared, which is 2, plus 1 cubed, 1, plus 2 times 1 to the 4, which is 2, plus c times 1, which is c, plus d, which we already found was 3. So we have 10 is equal to 2 plus 1 plus 2, 5 plus 3 is 8, 8 plus c, and that means c, subtract 8 from both sides, is equal to 2. Now we put everything together, and our function f of x is equal to 2x squared plus x cubed plus 2x to the 4 plus 2x plus 3. And if you wanted to, you could take the second derivative of this, make sure it matches up with what we're given at the beginning, and check this function to see if you plug 0 in for x, you get 3. If you plug 1 in for x, you get 10. I'm not going to do that because that's how we constructed it. Okay, next example. We're asked to find an expression that gives the value of the sum in terms of n. So, in order to do this question, we need some formulas. Write those formulas down. First formula is the sum from I equals 1 to n of a constant. C, that's a constant plus a constant, that same constant plus the same constant plus the same constant n times. We'll get c times n as a result. Next formula we'll need is the sum from I equals 1 to n of I. That's 1 plus 2 plus 3 plus 4 all the way up to n. We prove this one in class. We get n times n plus 1 all over 2. That was the grade 4 proof. And then we didn't prove this one in class, sum from I equals 1 to n of I squared. I said you can do it geometrically if you really want to. You have at least 2 or 3 pieces of paper just to work through stuff and draw pictures. Just quote the result. N times n plus 1 times 2n plus 1 all divided by 6. And you should have these 3 memorized. Okay, let's put them all together. See how they fit together. This sum will split up into 3 sums. This is the sum from I equals 1 to n of I squared, plus the sum from I equals 1 to n of I. We'll put the 3 in front. You can factor constants in out front. Plus the sum from I equals 1 to n of 4. You also bring the 4 up front and just put a 1 inside the sum, but it doesn't matter. Okay, the first sum we just quote the result, n times n plus 1 times 2n plus 1 all divided by 6. The second part, we'll have 2 times sum over I, that'll be 2 times n plus 1 all over 2. And at the last part, we'll have 4 times n. And if there's a multiple choice question, chances are the solution would not be the correct answer. You'd have to do some simplifying, you'd have to rearrange. But I'm not going to do that because who knows in what way you'd have to rearrange. You may just... Oh, made a typo. It's supposed to be a 3, not a 2. Anyway, you look for simplifications and cancellations, and you have to FOIL stuff out, and you have to collect like terms and all that good stuff. Okay, next question. I know you guys don't like these. It wants you to convert a sum into an integral, an infinite sum. And the key to doing these is to know that the integral from a to b of f of x dx, which is interpreted as the area under f of x from x is equal to a to x is equal to b, will be given by the limit as n approaches infinity of the sum from I equals 1 to n. We're going to add up a whole bunch of rectangles, in which the width of each rectangle is delta x, and the height of each rectangle is f of x sub I. Okay, now what are these things? Delta x is b minus a divided by n. So if you're going from a to b in n steps, the size of each step will be delta x, b minus a over n. So how much you're traveling and how many steps you have to travel that distance, that'll give you the step size. And x sub I are your sample points, where you're measuring the height of the function. You're starting at a, and you want to measure the function after taking I steps. So I times delta x will tell you how far in the x direction you've traveled after I steps. Okay, so we're looking at all these, and they all, as usual with these kinds of multiple choice questions, they all look connected, they all look reasonable. There's a few that we can exclude right away. For example, we can exclude d immediately, because its delta x would be 3 minus 1 over n, that would be 2 over n, and we have a 3 over n inside of our expression, so the d is gone. Likewise, e is gone for the same reason. Delta x is wrong. Now the other ones, they all have the correct delta x, so they're all 3 over n, and let's check the rest of this. So, I'm going to circle this piece. 3 over n is a delta x term. What's left over has to be your f of x sub I. So I'm going to propose that f of x is the square root of a plus I delta x, the square root of x sub I. So let's say that a is equal to 1. Then what's that mean? That's going to mean b minus a over n of delta x has to equal 3 over n. So the n's will cancel. We'll have b minus 1 is equal to 3. That means b is equal to 4. Okay? So our f of x sub I would be square root of 1 plus I times 3i over n. Well, it matches up perfectly with b. Because everything in here, that's x sub I. So f of x sub I is the square root of x sub I, and that means f of x is the square root of x, evaluated from 1 to 4. So choice B. The other ones don't match. They have the wrong f of x. They have the wrong function in there. The 3's are, in a sense, the 3 is counted twice and the a is counted twice. It's their double counted for choice C, and then for choice A, it's just all wrong. C is very tempting. Okay, next question, much more straightforward. Once you recognize that when you have a function, when you're asked for the derivative of a function that's in the base and a function that's in the power, so a function to the power of a function, f to the power of g, you need logarithmic differentiation. It's a differentiation strategy. In a sense, it's not like chain rule, product rule. Quotient rule isn't a direct rule. It's a strategy. You take the natural log of both sides, ln both sides. What makes this strategy work is a log property. The property that says the ln of a to the power of c is c times ln of a. Power comes down. So for our example, the power of the x comes down, comes out of there. Ln y equals x times the ln of the square root of x. I'm going to show you a trick. For this particular question, it's almost a one-off trick. Ln of the root of x is the ln of x to the 1/2, and the 1/2 can come down. So we have 1/2 times ln of x. So we haven't yet taken a derivative, we're just simplifying. We'll have 1/2 times x times ln of x. Okay, next thing. I'm going to put a bracket here. Because when we take the derivative of this expression, we have two functions on the right. We have to use a product rule. On the right-hand side. And on the left-hand side, we have an implicit derivative. So let's differentiate. The derivative of ln of y is y prime over y. 1 over y times y prime. From the chain rule, the stealth chain rule. And then right-hand side product rule, we have our first function, 1/2 of x, multiplied by the derivative of ln of x, which is 1 over x, which we derived a long time ago, before the midterm, I think, in the context of writing y equals ln of x in terms of an exponential function, and then using the derivative for that. Anyways, plus the second function, ln of x, multiplied by the derivative of the first. The derivative of 1/2 times x is 1/2. Now we want to get y prime all by itself, so we'll have y prime is equal to y times all that stuff. Y is, the color, y is at the very beginning. It's the same y. So we'll have square root of x to the power of x multiplied by stuff on the right hand side. It simplifies a bit. 1/2 of x times 1 over x, the x is cancelled top and bottom, so it's just 1/2 plus ln of x all divided by 2. That'll be your answer. One hallmark or highlight or feature of logarithmic differentiation is that your derivative will always contain your initial function multiplied by a product rule of some kind. So 2 terms times your original function. Okay, next example. Word problem. It says a helicopter is at a fixed height of 5 meters. So a fixed is a fancy word that means it doesn't change. It's constant. And so constant of 5. Above a landing pad, point A, and travels west at 1.5 kilometers per hour. The man is standing at point B, 4 meters east, and walks east at 0.5 meters per second. So the distance, the horizontal distance is changing. The vertical distance is not changing. At what rate is the distance between the man and the helicopter changing 4 seconds later? So this aspect, this 4 seconds later, that's going to require us to draw a second picture. So here's the second picture. The vertical distance is still 5. I'll call that vertical distance h. Now the horizontal distance has changed. It was 4, but in 4 seconds, the helicopter has moved 1.5 meters per second. So the total distance is 1.5 times 4. That's 6. So it gets a plus 6 distance. And then the man has moved to the right at 0.5 meters per second times 4 seconds. He's going to get a distance of plus 2. So we started with 4. We're adding 6 on the left side, 2 on the right side. That's going to give us a total horizontal distance of 12. I'll call that L. So at this instant, L is equal to 12. H is equal to 5. Also, H prime, the rate of change of the horizontal of the height, is 0. What's L prime, the rate of change of the length of this shape? Well, the helicopter is moving 1.5 meters per second to the left. The man's moving 0.5 meters per second to the right. They're both contributing to an increase in distance, so an increase in the horizontal distance. So the easiest way is just to add those two numbers together as a total change of 1.5 plus 0.5, so a total change of 2 meters per second. They're both adding a positive quantity. They're both making the distance larger. Don't worry about east versus west or left side versus right side. Don't try to set up your problems that way. Think about, is the quantity measured getting bigger or smaller? If it's contributing to an increase in the size of the quantity, it's a positive contribution. If it's contributing to a decrease in the size of the quantity, it's a negative contribution. Okay. Now we need a third part of our label, a third part of our diagram. We need to label the total distance between them. The distance between the man and the helicopter, I'll call capital D. It's the hypotenuse of that right angle triangle. Okay, next. Let's relate the variables together. D squared equals h squared plus L squared. That's going to allow us to do two things. It's going to allow us to find an expression that involves d prime, what we're after. What rate is the distance between the man and helicopter changing, so that's d prime, what we're after. It's also going to allow us to solve for what the distance is after 4 seconds. So after t equals 4, d squared is equal to h squared, which is 5 squared, plus L squared, which is 12 squared. So d is equal to the square root of 5 squared plus 12 squared. And lo and behold, a hint has been given for exactly this thing. So our distance is 13. Okay, now we're going to need that. Let's go back to the first time I wrote Pythagorean theorem. D squared is equal to h squared plus L squared. Let's differentiate that with respect to the hidden variable time, t. All of these are implicit derivatives. So we have a function to the power of 2. We take the derivative of that function to the power of 2. The 2 comes down. There's a function to the power of 1 multiplied by the derivative of the inside, the chain rule. And the same thing will happen for the two other pieces. 2 times h prime plus 2 times L prime. So some nice things happen. H prime is 0, so that first expression on the right cancels out. We can cancel the 2's on both sides. Okay, so then d prime is equal to L multiplied by L prime, all divided by d. So that's going to be 12 multiplied by 2 divided by 13. 24 divided by 13 in units of meters per second. Would be the rate of change of the distance. And that's our answer. Approximately 2. A little bit less. Okay, next one. Missing? No, everything's good. Next one. Find the absolute max and absolute min values of f of x on the given interval. This is important to identify with this word absolute. There's no number line here. You don't make the number line and look for increasing and decreasing. Your strategy for absolute max and absolute min is your extrema, if you have a well-defined endpoint, will either occur on the endpoints or at critical numbers in the interior. We're going to look for those critical numbers in the interior by taking the derivative of the function and setting that derivative equal to 0. The derivative of 6x cubed, 3 comes down, so we have 18x squared, plus the derivative of 18x squared, the 2 comes down, 36x, plus the derivative of 4 is a constant, so its derivative is 0. We set the derivative equal to 0 and solve for x. You can common factor out 18x from both pieces. On your quizzes, a lot of you made mistakes here with factoring. 18x out of x squared leaves us with an x. 18x out of 36x leaves us with a 2. We set that derivative equal to 0. That's going to have two solutions. 18x is 0 when x is 0, and then make the second part 0 if x is equal to negative 2. However, I was happy to see the vast majority got to this point correctly identified that you cannot use the second solution because it's not between negative 1 and 1. It doesn't count. Doesn't count. Now we're going to do what we did. The problem was that up here. For problem 1, we have the endpoints given. We found the critical number in the interior. Now we're going to plug in into the original function the endpoints and the critical number. F of 0, that's going to be 6 times 0 cubed, which is 0, plus 18 times 0 squared, which is 0, plus 4. So we get 4. Now we're going to plug in negative 1 into the function. We'll get 6 times negative 1 cubed, which is negative 6, plus 18 times negative 1 squared, which is 18, and plus 4. That'll give us 16. And finally, f of positive 1. That'll be 6 times 1, which is 6, plus 18 times 1, which is 18, plus 4, and that will be 28. Now we rank the y values. And the lowest y value is 4, the highest y value is 28. So from that we can say global min is at the lowest y value at 0, 4. And the global max is at the highest y value, which occurs when x is 1. And it gets a y value of 28. And that's our global max and global min on this interval. Next question. Before I do anything here, notice that there's a log function. And you can't plug negatives and you can't plug 0 into ln of x. So right at the very beginning, I'm going to state the domain. Domain is 0 to infinity. Okay, so if you take the derivative, or the second derivative, set equal to 0 and solve for x, and you get numbers that are not inside the domain of the function, they can't be critical points, they can't be regions of increasing and decreasing, or regions of concave up and concave down, because the function doesn't even exist there. This ln of x, its graph, the graph of this whole f of x function, starts at 0, or just to the right of 0, at 0 plus, and extends towards infinity. There's no piece of the graph 0 or left of 0. Okay, first, find regions of increase and decrease. That requires us to take the derivative of the function. The derivative of 1 times x is 1. The derivative of 1 over 6x squared, the 2 comes down, we get minus 1 over 3 x. And then minus the derivative of ln of x is 1 over x, so we have 2 divided by 3x. Common mistake I saw here was not properly addressing the fact that this x is downstairs and kind of sneaking it upstairs. for mysterious reasons, using new kinds of math I haven't seen before. Don't do that. Okay, we want to set this derivative equal to 0. Also want to check for places where the derivative does not exist, as long as the function does. So the derivative doesn't exist at 0, we'll be dividing by 0 in that last piece. But the function doesn't exist there either. It can't be a location of max or min. It could be a location where the function changes from increasing to decreasing, but we can't test to the left of 0. It's outside of the domain, so it's a moot point for this function. Okay, in order to set this equal to 0, it's easiest if we bring everything into a common denominator. So for the first term, multiply top and bottom by 3x. We have 3x over 3x. The second term, multiply top and bottom by x. So we'll have x squared over 3x. And for the third term, leave it alone. It already has this the correct denominator. Now we can multiply both sides by 3x. 0 times 3x is 0, and everything on the left is happy. Without the 3x on the bottom now. Okay, this is a quadratic. I'm going to rewrite it. I'm just going to move everything over to the left-hand side to make the x squared term positive. So x squared minus 3x plus 2 equals 0. This has two solutions. This is factors into x minus 2 times x minus 1. So we get two answers. X is 2 and x is 1. Both of these are in the domain of the function. So unfortunately, we have to draw a number line now and check in the three regions that will be constructed. Oh, I just screwed up the first part. It's not going from negative infinity to infinity, it's going from 0 to infinity. Okay, now we'll put down those magic numbers. Put down 1 and 2. We need test values now, test numbers. We need a number between 0 and 1. That's going to be 1/2, would work. A number between 1 and 2. That'll be 3 over 2. That'll work. And we need a number between 2 and infinity. Let's go with 3. And what do we do with these? We plug them into the first derivative of the function. So we're going to go back to this form of the function before we started messing with it. You can only plug into a factored form or into the original form. Once you start rearranging, moving stuff to across, and doing all kinds of stuff like that, you run some risks. For example, of having the wrong sign. If you move everything to the left side versus right side after setting equal to 0, you've just screwed it up. Okay, so let's evaluate our derivative, f prime, at the test value. We're going to diagnose what the function is doing, if it's increasing or decreasing inside each of the regions. 1 minus 1 over 6, 1/2 times 1/3 is 1 over 6. And then plug in 1/2 into the third piece of the derivative, 2 over 3x. So we'll have 2 over 3 times 1/2. That'll be 4 over 3. Okay, and 4/3 is larger than 1. So just without the 1 minus 1 over 6, 1 minus 4/3 is negative. Yeah, then you further subtract 1 over 6 from it, it's even more negative. So in this first region, the function is decreasing. And now we check the second region. 3 over 2 into the derivative. And we'll have 1 minus. Let's see. We'll have 1/3 of 3 over 2. That'll be 1/2. And then plug 3 over 2 into the second, or rather into the third piece of the derivative. We'll have 2/3, and then a 3 over 2 there, so that's going to be 4 over 9. Ooh, that's not very nice. But however, 1 minus 1/2 is 1/2. So those two terms combine. 1/2 minus 4 over 9. 4 over 9 is less than a half. 4 over 8 would be a half. So this is a number that is less. You have 1/2 minus something that's like 0.4. So 0.5 minus 0.4. That's going to be positive. And if you're not comfortable doing what I just did, bring everything to a common denominator, subtract, and then you'll know for sure. That what I just said confused you, just bring everything to a common denominator. Okay, next we're going to plug 3 into the derivative. So that's going to be 1 minus 1 minus 2 over 9. And that's definitely negative. 1 minus 1 is 0, and so subtract 2 over 9, it makes it negative. So we have decreasing, increasing, decreasing. So to say it verbally, because I'm running out of space, the function is decreasing from 0 to 1, increasing from 1 to 2, and decreasing from 2 to infinity. Next part of the question, looking for max and min. According to this picture, there's a min at 1 and a max at 2. So min at x is equal to 1, and max at x is equal to 2, but we're not done yet. You have to get the y values. Y is equal to, you plug into the original function, f evaluated at 1, that's going to be 1 minus 1 over 6 minus 2 over 3 times the ln of 1. Ln of 1 is 0, so 1 minus 6 minus 0. That's 6 over 6 minus 1 over 6, which is 5 over 6. And then for 2, we have y is equal to 2 minus 2 squared over 6, so that's 4 over 6 minus 2/3 ln 2. Ln 2 is just ln 2. Don't touch it. Don't do anything to it. 2 minus 4 over 6, that's going to be 2 minus 2/3. So that's 6, that's 4/3 minus 2 over 3 ln 2. Not a very nice number. Let me check that. 2 minus 2 over 3, that's going to be 6 over 3. Yes, okay, good. Very annoying. Okay, next piece. Part C. That part's asking for regions of concavity. And that requires the second derivative. And when you take the second derivative, I saw a few of you do this the wrong way. Don't take the second derivative from the simplified form after getting rid of that 3x on the bottom and rearranging to solve for how the function is equal to 0, or how the derivative is equal to 0. You can't start from there. You've changed the function by rearranging it like that. It's okay to factor the derivative and then take the second derivative from that, from the factored form, without changing anything else. But what happened at the end, the x squared minus 3x plus 2, that's not what f prime is. That's a rearranged and screwed with version of f prime. So I'm going to take the second derivative starting from what's been circled. Derivative of 1 is 0. Derivative of 1 over 3x is 1 over 3. And the derivative of minus 2/3 x downstairs, that's 2 over 3 multiplied by the x to the power of negative 1. You take the derivative of x to the negative 1, you get negative, what am I doing? So minus 2 over 3, and you'll get negative x to the negative 2. So it'll be 0 minus 1/3 plus 2 over 3x squared. So that's high school calculus stuff. If you don't like doing the derivative the way I just did it, use a quotient rule. You get the same thing. as long as you know that derivative of 2 is 0. Next, we're going to rearrange this to solve for x. Add 1/3 to both, set derivative equal to 0. Add 1/3 to both sides. So 1/3 is equal to 2 over 3x squared. The 3's cancel. Cross multiply by x squared. X squared is equal to 2. A lot of mistakes happened at this part. A lot of errors were made in solving for x. Next, it looks like we get two solutions. We get x is equal to root 2 and x is equal to negative root 2. But the second part, second solution, apparent solution, is not inside the domain of the function. You can't use negative values inside logs, so that doesn't really count. Next, we'll make our number line. Number line, see, I'm using more space than you guys had. I apologize. This question was really crammed in. Our number line goes from 0 to infinity, and it gets cut once at root 2. We're going to choose some test values next. We'll choose 1, and we'll choose 2. Root 2 is larger than 1, and smaller than 2. Root 2 is around 1.4. Now what do? Is we plug these test values into the second derivative. So f double prime of 1, that'll be minus 1 over 3 plus 2 over 3. That'll be 1/3, which is positive. So the first region is concave up. Now I'll check what happens if we plug 2 in. F double prime of 2. That'll be minus 1 over 3 plus 2 over 3 times 4, 12. And that's definitely going to be negative, because we're going to have 1 over 3 plus 1 over 6. That's negative 1/3 plus 1 over 6. So that's minus 2 over 6 plus 1 over 6. That'll be negative 1 over 6. So negative. So concave down. So it's concave down. First concave up on 0 to root 2, and concave down on root 2 to infinity. There's a point of inflection at root 2, POI at root 2, and the y value is the original function evaluated at root 2. That's going to be, let's see, root 2 minus 2 over 6. Root 2 squared is 2 minus 2 over 3 ln 2, ln root 2. And then that ln of root 2, you can write root 2 as 2 to the 1/2, bring the power down, and simplify if you want. I'm not going to bother. Leave it like that. You'd simplify it to match your multiple choice solution. Okay, and we'll continue with the next questions from 9 on in the next video.